There's the school project I need to make. We are supposed to work on it for 2 weeks, but I've been doing other stuff, which means I have to do it, well, today. I have this pendulum which swings. I need to use sensors to record this angle theta. Then if I plot the theta against time, it's gonna look something like this, where the amplitude gets lower and lower as the oscillations dampen. And based on how much these oscillations dampen, I should calculate the damping ratio. This is for my signal processing class, so the main thing is gonna be measuring this angle with various sensors and then processing the data to get a decent graph of theta versus time. This might not sound too interesting, but I decided to make this video for 2 reasons. Firstly, it's quite useful, and I'm probably gonna use IMU and these sensors in my robotic dog. The second reason I'm gonna talk about later. To measure the angle directly, I'm gonna use a magnetic encoder, which you'll see in a minute. I'm also gonna measure the angle with IMU. The IMU measures acceleration in 3 axes, and it measures angular velocity also in 3 axes. So I'm gonna use the IMU to guesstimate the angle. This will be a great setup for the future, because I will definitely use this for the robotic dog. The signal processing part is also going to be interesting. There are many possibilities. There's a low pass filter, which is quite boring, but very useful. I actually use this for my hexapod. It's when you have noisy data and you want to smooth it out. So if this was a sine wave, the low pass filter would do something like this. There's also Kalman filter, which is more complicated. And there's also a complementary filter, which I will probably use. I bought the sensors about 2 weeks ago, so I'm gonna prepare them and we're gonna build the pendulum. This is the magnetic encoder. It's called AS5600. I'm just soldering some pin headers to it, so I will be able to connect it to Arduino easily. Since we live in modern times, I just asked ChatGPT to provide me with the wiring diagram. Okay, I got this encoder magnet. It has poles arranged radially, so when I rotate the magnetic field also rotates, which is read by the encoder. If you look at this graph, you can see it's absolute trash. That's because my hand shakes and the axes aren't aligned. There also needs to be a precise distance between the magnet and the encoder, but I just wanted to check that I wired it correctly. I've made this really shitty attachment for the encoder. There's not much space because of the pin headers, so it was really hard to make. Like, inserting the heatset inserts was quite painful. So this turned out awfully. Yeah, this works. It's good enough, I guess. Alright, the encoder is wired, the mount has been printed, so now I'm gonna add this GY521 IMU, which is a 3-axis accelerometer and gyroscope. I'm gonna solder pin headers to it, I'm gonna wire it up and make sure it works. I was wondering how the IMU works, because it's not obvious to me how you would measure angular velocity. So I watched some videos and it seems that the angular velocity is measured with the Coriolis effect. So you have a mass that's vibrating in one axis, and when you start rotating the system, it also vibrates in the other axis. This can be measured and the angular velocity is calculated from this. For the accelerometer, this is more straightforward. You have a proof mass, which is free to move, and electrodes that are stationary. When you exert acceleration on the system, the mass moves to one side or the other, and this changes the capacitance of the system, which can be measured, and the acceleration is calculated from that. For the wiring, I used ChatGPT again, and to write the actual Arduino code, you can guess that I also used ChatGPT. Now I'm just testing the IMU. You can see that when I rotate it, the angular velocity in my code changes. By the way, I'm measuring the angular velocity only in a single axis, because that's all I need for the pendulum. This is my shitty little pendulum. It weighs almost nothing, so when I try to swing it, it stops really quickly. I was expecting this, so I added this hole in which I can put a screw or something to add weight. The Arduino with the breadboard are gonna sit here, and the IMU is gonna be attached to the pendulum, but these cables are too stiff because the pendulum weighs next to nothing, so even when I add weight, it affects the swinging, so I'm gonna make the cables longer. By the way, this isn't the ideal way to do it, like using these cables, and this is also kind of trash, but it's for a school project, so I'm not gonna put too much effort into it. Because of my shitty design, the bolts were inaccessible, so it was super painful to screw them in. Yeah, this is pretty fucking awful. The wires affect the swing too much, so I'm gonna make the pendulum 2 times as long, and I'm gonna add more weight. I've made the pendulum longer, I added more holes so I can make it heavier. The IMU should sit flush with the pendulum, but it doesn't because of these pins, so I added a hole. And I also improved this joint to make it wiggle less. Despite the looks, this is a pretty shitty setup. I'm moving the pendulum, my PC is reading the signals from the Arduino, and it's plotting them in the terminal. This thing is fucking horrible. The encoder isn't positioned well because I use these long bolts. The pendulum vibrates like crazy, which is horrible for measurement. This needs to be precise, which is not. I should have just used a bearing, but I thought it wouldn't provide enough friction, I don't know. This is so laughably bad, I should definitely remake it. But when I'm gonna present this, they are not gonna see the video, so I'm not doing that. I haven't recorded the actual measurement, but this is the data from the encoder, and if you're wondering how I got this nice data out of this trash, it was pretty tough, but I managed to do it. So this doesn't really swing, it works only for small angles, and the data coming out of this is fucking horrible, because if you look at it, it vibrates in this axis. So I solved this problem by tilting this, then it doesn't vibrate as much, and I was able to get this nice data out of it. This IMU provides quite a bit of data, and I won't need all of that, so I'm gonna show you exactly what I'm gonna measure. I'm gonna measure 2 accelerations, one in the x-axis and one in the y-axis. Then I'm gonna measure the angular velocity. I'm also gonna measure the angle with the encoder. So I'm measuring 4 values. I won't need to measure the time because my code runs in a loop and there's a 50 millisecond pause. So the time vector is gonna have increments of 50 milliseconds. Okay, now I'm gonna plot the data I got out of the pendulum. This is my Python code. It's kind of boring, so I'm just gonna speedrun it. I imported the data from the text file. I changed the units to meters per second squared for the acceleration. I added the time vector in the 50 milliseconds increments. And now I'm gonna plot the encoder angle. This is what the angle looks like. It's nice, but you can see that it starts at 60 degrees. When I inserted the encoder magnet, I just put it in a random orientation. I didn't measure the magnetic field, so I need to subtract this first angle, so it will oscillate around 0. That's this angle offset. I just take the first value and then I subtract it from the data. And now it oscillates around 0. So this data is really good. Measuring it with the encoder is easy, but if I had a drone, for example, I couldn't measure it with an encoder because the drone isn't attached to the ground. So now I'm gonna use the data from the IMU and I'm gonna try to get this same graph with the data. This video is sponsored by PCBWay, which is pretty sick. I mean, imagine doing your math homework and getting paid for it. That's kind of what I was shooting for. These sponsored videos are the reason I was able to afford this nice camera, and I also don't have to worry about budget for my larger projects, so thank you guys for the support. I use PCBs for pretty much everything. I've used them for my hexapod and I'm gonna be using them for my robotic arm. Here it didn't quite make sense because it's just a small school project, but anything bigger than this, you want to use PCBs. It will save you so much time because all of this can be compressed into a nice little circuit board. If it's your first time using PCBWay, you get a $5 bonus. They also do CNC machining, injection molding and other stuff. I think they even sell oscilloscopes, which is pretty sick. Okay, let's address the integral in the room. If you look at this IMU, it's not measuring the angle, it measures angular velocity. So we need to get angle from this data. If the velocity was constant, it would be easy, because the angle would be just the velocity times time. But this works only if the velocity is constant. If we plot this out, it would look something like this. So you have the constant velocity, and if you multiply the velocity by the time, you get the angle. So it's actually an area of this rectangle. But our velocity is not constant, it looks something like this. And it's the same thing, right? If we wanted to calculate the angle, it's gonna be the area under this curve. But now we can't use this formula because it's not constant and there are no rectangles. But we can make a decent approximation. I'm gonna draw the first peak. So to calculate the angle for this time, we just need the area under this first peak. And to calculate the area, we can divide this into many rectangles. So it might look something like this, and if we compare these two areas, it's gonna be pretty similar. You should get used to these approximations with engineering. And now, since this is a bunch of rectangles, we can calculate the area easily. If you look at one of these rectangles, the height of this rectangle is just the omega, and the base of this rectangle is just the time. I'm gonna call it delta t because it's just a small change in time. This small change in angle is just the velocity times the small change in time. And we can calculate this change in angle for all of these rectangles. And if we sum it up, we're gonna get the theta for this first peak. We can do this for the whole curve and get the angle that way. This is called an integral, and in the code we can just use a function that's gonna calculate it. To get the angle out of the gyroscope, I just use integration. I integrated the angular velocity and I got this graph. You can see that this data looks similar to the encoder, but it has a downward trend. And this is to be expected. I'm gonna show you where this comes from and how I'm gonna get rid of it. The data should look like this, but when we integrate the velocity, we get this. Let's say we wanted to measure this object's position, and we had a sensor that's measuring the velocity. So we want to know the position x, and this sensor measures velocity vx. Position is just velocity times the time. So if the sensor gives us 0 for the velocity, the position is not going to change and it's just going to be 0. When you measure anything, there's always an error. It's never perfect. Let's say that the sensor has an error of 1. So when this object is not moving, the velocity according to the sensor is 1. That means that the position is going to be 1 times t. If you plot this out, as the time increases, the error in the position is also going to increase. And this is exactly what's happening here. There's an error in the gyroscope, so when we integrate the angular velocity, we also integrate the error. Now if we add these two graphs, instead of the perfect data, we get this downward trend. Okay, we got the angle out of the encoder, which is great, but if this were a drone, we couldn't use an encoder. Then we got it out of the gyroscope, which is great, but it has a downward trend. And now we're gonna get it out of the accelerometer data. Let's assume the pendulum is at an angle theta. This is how the IMU is oriented. And let's also assume that the angle doesn't change, so the pendulum is at a constant position. In this system, the only acceleration is gravity. Now we can draw the accelerations the IMU would measure. Since this is theta, this angle is also theta. And since these two are parallel, this angle is also theta. Now we can use the measured accelerations to get the theta angle. So this is great, but it only works if this angle theta is constant, which it's not. Since the pendulum swings, there's gonna be some centripetal force towards the center of rotation. I'm gonna call it AC for centripetal acceleration. So the total acceleration acting on this pendulum is gonna be G plus the acceleration from the centripetal force. So now the IMU isn't measuring this acceleration in the y direction, but it's measuring this acceleration. So the angle theta is gonna have some error in it. I think, don't quote me on this, this is what I've thought of right now. This should give us estimation of the angle, but it probably won't be too good. So we're gonna combine the data from the gyroscope and from this accelerometer, and we're gonna get a decent estimation of the angle. I calculated the angle from the accelerometer data in the code, and if we plot this out, you can see that it kind of works, although there's a lot of noise in the data, and it's also very inaccurate. Like if you look at this third peak, here the angle is something like 10 degrees, and here it's almost 20. If we compare it to the gyroscope data, we can see that both of these graphs aren't great. If you look at the gyroscope data, short term, this is a pretty decent estimation, but over time the error grows bigger and bigger and it diverges. On the other hand, if you look at the accelerometer data, short term this is awful. If you look at this first peak, it jumps to negative 20 degrees for some reason, but long term, here the angle is kind of around 0, while for the gyroscope it's minus 15 or something. So we can combine the benefits of both of these sensors and get a decent estimation for the overall angle. This is a perfect job for a complementary filter. I'm gonna explain the complementary filter first in the block diagram and then in the code. So even if you've never seen a block diagram, you're gonna see it in the code. I'm gonna start with the gyroscope data. We take the angular velocity from the gyroscope, multiply it by the change in time, and we get the change in angle. To get the overall angle, we need to add this change in angle to the previous angle. That's what this X means. It means that these two signals get added up. And from this we get a new estimate for the angle. I'm gonna call it theta here for estimation. We feed this estimate to the next time step, and the notation for this is just 1 over z. So this loop says that we take the velocity, multiply it by the change in time to get the change in angle, and we add this change in angle to the previously estimated angle to get the new estimate. This is how the cumulative integration works in Python, it's just in block diagram. And this is how we calculated the gyroscope angle. Now we are gonna add the data from the accelerometer. From the accelerometer we get the calculated angle, and we want to combine this with the angle from the gyroscope. We can take, for example, 90% of this gyroscope angle. So we multiply it by 0.9, and we take the complement of this, which is 0.1, and add these two signals up. So we take 90% of the gyroscope angle and only 10% of the accelerometer angle. Then we get a new estimate and feed it to the next time step. For the gyroscope data, most of it makes it out, and for the accelerometer only a slight amount of it gets passed down. And this is also a low pass filter, so we are letting only the low frequencies of this accelerometer data pass through. Okay, now I'm gonna show you the code, which will probably be simpler to understand. If you want a better explanation of this filter, you can check out Brian, I will link him in the description. Now for the code, we first estimate the angle to be 0. In a for loop, we calculate the angle from the gyroscope to be the previously estimated angle plus the change in angle from the gyroscope. And we calculate the complementary filtered angle to be 90% of the gyroscope angle plus 10% of the accelerometer angle. The orange curve is the encoder angle. I'm assuming it's accurate, so that's what I'm comparing the filtered angle to, which is the blue curve. You can see it's pretty similar, so we did a good job. And now we can really see what the complementary filter does. It captures the short time data from the gyroscope, and to get rid of this downward drift, it uses long-term data from the accelerometer. I think this filter is great. It's quite easy to code, it's just these 3 lines. The results are great also. So I'm probably gonna use this in a robotic dog or something to estimate the state of the robot, like its orientation. And yeah, this project is finished. This was the main part. I also implemented extended Kalman filter, but I think I probably fucked it up, so I didn't show it in this video. Now I'm gonna present it in front of my class and see what I got.